All right, now let's look at what's happening at point B of the roller coaster cart's trip through the loop. So from point A to point B, what we see is the normal force is still pushing inward on the cart, providing a centripetal force. But less and less of the force of gravity is in the radial direction. And by the time you get to point B, gravity is actually fully in the tangential direction. So that means slowly as you go from A to B, gravity is doing work against the cart, causing its velocity and its speed to change and to decrease, to be specific. So if I want to find the linear speed of the ball at point B, it's really hard to use dynamics because the acceleration is constantly changing from point A to point B. But again, when we have curves and we have changes in elevation, just like we did first semester, we're going to want to apply conservation of energy in order to model and solve these types of problems. So for the first one, finding the linear speed at A, at B, remember that we knew the linear speed at A was 25 meters per second. And so if we look at what changes from A to B, and we apply conservation of mechanical energy, remember we're ignoring resistive forces in this scenario, we know that the change in mechanical energy as I go from A to B has to be 0. So whatever mechanical energy I have at A, I must also have at B. So now at A, I'm at the lowest point of the ride, so we're going to call that our 0 joule potential mark. So I have only kinetic, 1/2 m VA squared. But by the time I get to B, I've increased my height, and the height that I've gone now at point B is the actual radius of curvature. So I have now mg hb, which is just r, plus 1/2 m v at b squared. So because of the increase in potential energy, gravitational potential from A to B, I'm going to have a decrease in speed. So we can model this using conservation of energy. So if we do the math and solve it through using the algebra here, I'm going to do a quick shortcut. We find that VB will be the square root of VA squared minus 2GR. Check the algebra, which means VB will be 20.7 meters per second. So as we go from A to B, we lose linear speed because of the fact that gravity is now doing work against the cart as it goes up the hill. And use conservation of energy to find that new speed. But alas, we are still moving in a circular path. So at the moment we're at point B, I can still use this to figure out the angular velocity, the centripetal acceleration. Because now we know that v at that instant is 20.7 meters per second. So we can go back and say, oh, well, omega at point B will just be VB divided by the radius, or now 20.7 meters per second over 10 meters, which is now 2.07 radians, per, I'm not drawing that well, rads per second. So notice that's decreased as well. I'm not rotating as quickly because I've lost speed. My centripetal acceleration should also have decreased. So at that point, it's going to be dependent upon the linear speed at that moment divided by the radius, which will be my 20.7 meters per second squared over 10 meters. So my centripetal acceleration is now 42.9 meters per second squared. And if I'm calling inward negative, you can call AC negative. Just be consistent in however you set up the problem and think about it. All right, so this is decreased because at point A, I think it was 60. Well, let's see, let's go back. 62.5. So my centripetal acceleration has decreased because I have a slower speed, by the time I get to B. What about the tangential acceleration of the car at point B? Because what we said was, as the car goes more and more vertical, gravity is acting in the tangential direction. So if I want to figure out what is the tangential acceleration at point B, all I need to know is what is the net tangential force acting at point B and apply Newton's second law, just like I did for the centripetal direction. So if we see at point B, the only force acting on the cart in the tangential direction is gravity, and it's acting in the negative tangential direction. So if I say sum of the forces tangential at point B is mass times the tangential acceleration divided by mass, I get that the tangential acceleration will be Fg, which is acting in the negative direction, divided by the mass. Well, this is just mg over m. So my tangential acceleration at point B is just the acceleration due to gravity, because it's the only force acting in that direction at that point. Okay, last but not least, what is my normal force at point B? Now, notice the normal force at point B is my centripetal force. It's the only force acting towards the center of the circle, driving the curvature of the cart around this bend, causing its velocity to change inward. And so I have to apply Newton's second law in the radial direction, where normal force is equal to m times the centripetal acceleration. Well, we already found that in a previous problem. So now if we don't know this already, we can use the v squared, vb squared over r. But since we already know AC, normal is simply the mass of the cart, 500 kilograms, times the centripetal acceleration, which is 42.9 meters per second squared. And that's going to be a value of 21,450 newtons. Notice, normal force has decreased as you go from point A to point B because your centripetal acceleration is less, because you're moving at a slower speed.